Beyond the orbit of Neptune, where sunlight grows thin and the solar wind whispers against cosmic dust, a dark speck moves through space with the patient inevitability of gravity itself. This visitor carries no name yet, only a catalog designation that astronomers will assign once they confirm its trajectory, a string of letters and numbers that fails to capture the profound journey encoded in its ancient ice and stone. The designation 3I/Atlas will eventually grace scientific papers and conference presentations, but for now it remains simply an anomaly in the data, a slight deviation from the expected emptiness of interstellar space. The object tumbles slowly as it travels, completing one rotation every 7 hours and 38 minutes, a period that speaks to its irregular shape and the complex gravitational torques that have influenced its spin over millions of years. Its surface, darker than charcoal and twice as old as our planet, reflects barely 3% of the starlight that touches it. This darkness speaks of eons spent absorbing cosmic radiation, of molecular bonds broken and reformed in the endless cold, of a surface sculpted by impacts too small to register on any earthbound instrument, yet significant enough to gradually reshape its contours over geological time. Scientists know that interstellar objects like this one originate in the outer regions of distant planetary systems, ejected by gravitational encounters with giant planets or close stellar passages. The mathematics of orbital mechanics suggests that roughly one such visitor should pass through our solar system each year. Though most remain undetected, silent wanderers carrying their stories through our cosmic neighborhood without acknowledgement or witness. Statistical models indicate that at any given moment, dozens of these dark travelers move through the space between planets, invisible to all but the most sensitive instruments and most dedicated observers. What strikes astronomers about this particular visitor is its pristine nature, the way it appears untouched by the warming influence of any star for millions of years. Its spectrum reveals the signatures of materials that formed in temperatures near absolute zero, compounds that exist only in the deepest cold between stars. Here, frozen in crystalline structures more perfect than any laboratory can achieve, lie molecules that remember the conditions of interstellar space itself. Carbon monoxide ice that preserves the isotopic ratios of the molecular cloud where it condensed. Nitrogen compounds that formed in regions where starlight never penetrates. The object's trajectory tells its own story, carved into the mathematics of its motion with the precision of celestial mechanics. Computer models suggest it has wandered the galaxy for perhaps 5 million years, following a path shaped by the gravitational influence of dozens of stars. Each stellar encounter nudged its orbit slightly, a cosmic pinball game played across distances that dwarf human comprehension. The most recent significant perturbation occurred roughly 800,000 years ago, when it passed within 10 light-years of a red dwarf star, receiving just enough gravitational deflection to alter its course toward our solar system. Now, purely by chance, or perhaps by some statistical inevitability written into the structure of galactic dynamics, its path intersects with our solar system's gravitational embrace. The probability of such an encounter falls somewhere near 1 in a trillion for any given object over the span of 1 million years. Yet the sheer number of wandering bodies scattered throughout the galaxy makes such meetings not just possible, but virtually certain on cosmic timescales. As it crosses the heliopause, that invisible boundary where the solar wind meets the interstellar medium, subtle changes begin. Particles streaming from the sun encounter its surface for the first time in geological ages, each impact depositing energy measured in electron volts, warming materials that have existed at temperatures barely above absolute zero since before complex life evolved on Earth. The interaction creates no visible effects yet, but instruments sensitive enough to detect single photons register the faintest warming, the beginning of a transformation that will gradually awaken chemistry that has slept since the object's ejection from whatever distant system gave it birth. The visitor's composition remains largely mysterious. revealed only through the careful analysis of reflected sunlight passed into its component wavelengths by spectrographs attached to the world's most powerful telescopes. These observations suggest a mixture of water ice, carbon-rich compounds, and silicate dust, the fundamental building blocks of planetary systems throughout the galaxy. Methane and ammonia ices appear in the spectral signatures, along with more complex organic molecules that hint at chemical processes occurring in the cold darkness between stars. Yet something in these measurements troubles researchers. A subtle wrongness in the ratios that doesn't quite match the expected signatures of comets formed in our solar system's outer reaches. The carbon-to-oxygen ratio appears slightly elevated, and certain rare isotopes show abundances that differ from solar system norms by small but statistically significant amounts. This discrepancy might mean nothing. Natural variations in composition occur throughout the galaxy as different stellar environments produce different mixtures of elements through varying processes of nucleosynthesis and chemical evolution. Or it might hint at something more intriguing: evidence of chemical processes that occur only in interstellar space, where cosmic rays interact with ice and dust over millions of years to create compounds impossible to replicate in laboratory conditions. Perhaps the signature indicates formation in a stellar environment unlike our Sun, around a metal-poor star in the galaxy's outer regions, or in a system where supernova shock waves enrich the local chemistry with unusual elemental abundances. The uncertainty creates a quiet tension in astronomical circles, a question that observations alone may never fully resolve. Each new spectrum adds data points to the growing collection of measurements, but the fundamental mystery of origin remains. Scientists find themselves in the peculiar position of studying the most pristine samples of interstellar material ever encountered, while simultaneously watching those samples transform under solar radiation, destroying the very evidence they seek to preserve. What remains certain is the object's extraordinary journey. The simple fact that materials formed around a distant star now move through our solar system carrying information encoded in their very atoms. Isotopic ratios frozen into its ice tell stories of nucleosynthesis in stellar cores billions of years ago, when massive stars converted lighter elements into heavier ones through fusion processes that lasted mere millions of years before ending in spectacular supernovae. Organic compounds within its matrix preserve the chemical conditions of the molecular cloud where it condensed, a stellar nursery where turbulence and magnetic fields shaped the distribution of dust and gas across light years of space. The visitor serves as a messenger, delivering data about galactic processes across distances that light itself requires millennia to traverse. Its very existence proves that planetary systems throughout the galaxy lose material to interstellar space, contributing to a vast reservoir of wandering objects that carry chemical information between stellar neighborhoods. This cosmic recycling operates on timescales that reduce the history of human civilization to a fleeting moment. Yet, it connects our local stellar environment to processes occurring throughout the Milky Way. Perhaps most remarkably, this cosmic messenger arrived unannounced and will depart the same way. Its presence detected only because human technology has recently achieved the sensitivity required to spot such dark, distant objects against the background glow of zodiacal light and stellar radiation. For millions of previous years, similar visitors may have passed through our solar system completely unnoticed, carrying their stories through our cosmic neighborhood in perfect silence, their chemical wisdom remaining locked in darkness, while Earth's biosphere evolved from simple bacteria to complex ecosystems entirely unaware of these ancient wanderers. The object continues its approach, following the mathematical certainty of Kepler's laws, while simultaneously embodying the profound uncertainty of cosmic evolution. Its hyperbolic trajectory ensures that this encounter with our solar system represents a brief interruption in a journey that began before the formation of Earth's oldest rocks and will continue long after our Sun exhausts its nuclear fuel. The visitor carries no awareness of these temporal scales, no recognition of its role as a messenger between stellar civilizations separated by impossible distances and incomprehensible time spans. The visitor's path through space carries the signature of stellar encounters stretching back across galactic time. Each gravitational interaction recorded in the subtle mathematics of its trajectory, like growth rings in an ancient tree. Astronomers who trace its orbit backward through computer simulations discover a history written in orbital mechanics, a series of close approaches to stars whose names exist only in catalog numbers, whose light reaches Earth as anonymous points in constellation patterns that humans have watched for millennia without knowing their role in shaping this wanderer's destiny. The process of reconstructing this cosmic genealogy requires sophisticated numerical integration techniques that account for the gravitational influence of every significant mass in the galaxy. Supercomputers run simulations across millions of years of galactic evolution, tracking the visitor's probable path through a stellar neighborhood that has rotated multiple times around the galactic center since its journey began. Each calculation must account for the motion of individual stars, the gradual drift of stellar associations, and the complex gravitational architecture of spiral arms that rise and fall over periods measured in hundreds of millions of years. 5 million years ago, the object likely orbited a star in the galactic disk, perhaps 40 parsecs from our current location, in a region where stellar formation had ceased long before Earth's continents assembled into recognizable shapes. That parent system may have harbored planets, rocky worlds that never knew life, gas giants whose atmospheric storms raged for billions of years in perfect solitude, or intermediate mass planets whose geological processes created and destroyed mountain ranges while biological evolution remained forever absent from their surface chemistry. The ejection mechanism itself represents one of the most common, yet poorly understood processes in planetary system evolution. Theoretical models suggest that most planetary systems experience periods of orbital instability as their constituent worlds gradually modify each other's orbits through gravitational interactions accumulated over millions of years. These instabilities can persist for extended periods, creating zones of chaotic motion where small bodies follow increasingly eccentric orbits until random encounters provide sufficient energy for escape velocity. The mathematics of such interactions follow precise rules discovered by Newton and refined by centuries of subsequent observation, yet their outcomes remain essentially unpredictable for individual objects. Chaos theory governs these encounters, where microscopic differences in initial conditions, a slight variation in orbital phase, a marginally different impact parameter, produce vastly different final states across the vast scales of astronomical time. The visitor's ejection represents one possible outcome among countless alternatives, a single realization of probability distributions that extend across entire stellar populations. Computer models indicate that the ejection velocity likely fell within a narrow range determined by the mass distribution of the parent system and the specific geometry of the encounter that provided escape energy. Objects ejected too slowly remain bound to their parent stars in highly eccentric orbits, while those receiving excessive velocity escape with such high speeds that subsequent stellar encounters have minimal influence on their trajectories. The visitor's moderate ejection velocity allowed stellar gravity to gradually modify its path, creating the complex orbital history that eventually directed it toward our solar system. The object's subsequent journey through interstellar space involved dozens of stellar encounters, each one recorded in the gradual evolution of its orbital parameters. A close approach to a red dwarf star 800,000 years ago altered its velocity by less than 1 kilometer per second, a change barely perceptible on human scales, yet sufficient to redirect its path across dozens of light years over the intervening millennia. The cumulative effect of these interactions resembles a three-dimensional random walk guided by the gravitational architecture of the galaxy itself. Statistical analysis of the visitor's trajectory reveals that it has experienced approximately 30 significant stellar encounters during its interstellar wandering, with significant defined as approaches within 50 astronomical units of stellar surfaces. Each encounter produced measurable changes in orbital velocity, typically amounting to fractions of a kilometer per second, but accumulating over time into substantial trajectory modifications. The most dramatic encounter occurred roughly 2 million years ago, when the object passed within the outer regions of a binary star system, receiving gravitational deflection that altered both its speed and direction of travel. During its wandering, the object experienced the full spectrum of interstellar environments, from the warm, tenuous gas surrounding young stellar associations to the cold, dense molecular clouds where new stars eventually form. Each environment left its subtle signature in the surface chemistry, as cosmic rays and stellar winds gradually modified the composition of exposed materials. The warm interstellar medium, with temperatures reaching several thousand Kelvin and particle densities of roughly 1 atom per cubic centimeter, provided minimal direct heating but allowed high-energy photons to penetrate surface layers and drive photochemical reactions. Dense molecular clouds presented more dramatic conditions, with temperatures dropping to barely 10 Kelvin above absolute zero, while particle densities increased by factors of thousands. These environments effectively shielded the visitor from cosmic ray bombardment while allowing complex chemical reactions to occur on grained surfaces where simple molecules combine to form more elaborate organic compounds. The object likely spent roughly half its interstellar journey within such clouds, accumulating chemical modifications that reflect the specific conditions of star-forming regions throughout the galactic disk. What puzzles researchers is the object's apparent resistance to these transformative processes, as if something in its composition or structure provided unusual stability during its interstellar journey. Most theoretical models predict that objects exposed to cosmic radiation for such extended periods should show more dramatic chemical alterations, with organic compounds degraded by high-energy particles and ice structures recrystallized by thermal cycling between different interstellar environments. The typical cosmic ray flux in interstellar space delivers enough energy to break chemical bonds and rearrange molecular structures on timescales of millions of years, yet spectroscopic observations reveal surprisingly pristine materials, suggesting either exceptional preservation conditions or formation processes that produced unusually stable chemical configurations. One possibility involves the object's internal structure, which may contain sufficient mass to provide self-shielding against cosmic ray penetration. Alternatively, its surface composition might include materials that naturally resist radiation damage, perhaps through chemical configurations that rapidly repair molecular disruption or through crystalline structures that channel energy away from vulnerable chemical bonds. The visitor's approach to our solar system occurs at a time when astronomical technology has reached the threshold necessary for detailed study of such objects. Ground-based telescopes equipped with adaptive optics systems can now track objects barely a few kilometers across at distances measured in astronomical units, while space-based infrared instruments detect thermal emissions too faint for previous generations of detectors. This technological convergence transforms previously invisible wanderers into accessible subjects for scientific investigation, opening new windows into the chemical and physical processes that shape interstellar space. Advanced spectrographic techniques allow astronomers to detect absorption features corresponding to specific molecular transitions, revealing the presence of water ice, carbon monoxide, carbon dioxide, and more complex organic compounds frozen into crystalline matrices that preserve information about formation conditions. Each spectral line provides constraints on temperature, pressure, and chemical activity, allowing researchers to reconstruct the history of materials that formed under conditions utterly different from anything experienced within our solar system. Radio telescopes join the observation campaign, listening for any electromagnetic emissions that might distinguish artificial objects from natural ones. The search protocols developed for the search for extraterrestrial intelligence find new application in examining interstellar visitors, as scientists systematically rule out technological signatures while documenting the natural radio emissions produced by chemical processes occurring in the object's developing coma. These emissions, typically generated by molecular transitions in excited gas around active cometary nuclei, provide additional data about composition and internal structure inaccessible through optical observations. The object's brightness variations, measured with photometric precision impossible just decades ago, reveal details about its rotation and shape that constrain models of its formation and evolution. The light curve shows characteristic patterns indicating an elongated body tumbling through space, with surface features or compositional variations creating subtle modulations in reflected sunlight. These observations require weeks of continuous monitoring, as the rotation period stretches across multiple Earth days and the brightness changes remain barely detectable above instrumental noise levels. Professional and amateur astronomers worldwide contribute to the photometric campaign, creating a distributed network of observers that maintains nearly continuous coverage despite Earth's rotation and weather patterns. The collaborative effort generates datasets with temporal resolution and precision that no single observatory could achieve, transforming the visitor's light curve into a detailed portrait of its physical characteristics and rotation state. Spectropolarimetry adds another dimension to the analysis, as polarized light scattered from the object's surface carries information about grain size, composition, and surface roughness at microscopic scales. The technique reveals that much of the surface consists of fine, particulate material, perhaps created by eons of micrometeorite bombardment or thermal cycling, overlying a more consolidated interior that preserves the original chemistry of formation. This layered structure suggests a complex history of surface modification occurring during the long journey through interstellar space. The visitor continues its steady approach, following mathematical predictions with the reliability that first convinced ancient astronomers that celestial motions operate according to discoverable natural laws. Its path represents the intersection of individual cosmic history with the broader currents of galactic evolution, a single trajectory among billions that collectively shape the chemical and physical structure of interstellar space. As solar radiation intensifies with decreasing distance, the visitor's surface begins to respond to energy it has not experienced in millions of years. The warming occurs gradually, measured in fractions of degrees per day, as photons penetrate the dark, porous material that forms its outermost layers. This surface, sculpted by eons of cosmic ray bombardment and micrometeorite impacts, presents a complex landscape of microscopic peaks and valleys that trap solar energy with surprising efficiency despite reflecting only 3% of incident light back into space. The first materials to respond are the most volatile. Carbon monoxide ice buried just beneath the surface, formed during the object's passage through dense molecular clouds where temperatures dropped to barely 10 Kelvin above absolute zero. These deposits begin sublimating at temperatures still far below the freezing point of water, creating the first tenuous wisps of gas that escape the visitor's minimal gravitational field. The process follows well-understood thermodynamics, yet each escaping molecule carries information about chemical conditions that existed during formation processes occurring light-years from any star. Spectroscopic analysis of this early outgassing reveals isotopic ratios that differ subtly from solar system norms, providing evidence of nucleosynthesis processes that occurred in the stellar environment where the object formed billions of years ago. The carbon-12 to carbon-13 ratio shows slight enhancement of the heavier isotope, suggesting formation in a region enriched by previous generations of massive stars that processed light elements through nuclear fusion before dispersing them through supernova explosions. These isotopic signatures survive eons of interstellar wandering, preserved in crystalline structures that resist alteration even under cosmic ray bombardment. The outgassing creates forces that influence the visitor's trajectory in ways barely detectable with current instrumentation. Each molecule that escapes carries momentum, producing tiny rocket-like accelerations that accumulate over months to create measurable changes in orbital parameters. These non-gravitational forces typically amount to less than 1% of solar gravitational acceleration at the object's current distance, yet their persistent nature allows them to modify trajectories significantly over extended periods. Detecting and measuring these subtle effects requires astrometric precision approaching the theoretical limits of ground-based observations. What surprises researchers is the asymmetric nature of the outgassing, which appears concentrated in regions that correlate with the object's rotation period rather than its subsolar point. This pattern suggests internal structure more complex than simple conductive heating models predict, perhaps involving subsurface cavities where volatile materials accumulate before venting through preferred pathways to the surface. The phenomenon resembles jet activity observed in solar system comets, yet occurs at temperatures and volatile compositions unlike anything previously studied in detail. Computer models attempting to explain the outgassing patterns must account for heat diffusion through materials with unknown thermal properties, volatile transport through porous media under varying gravitational and radiation conditions, and chemical reactions between different ice phases as temperatures gradually increase. The calculations reveal that even small changes in assumptions about surface composition or internal structure produce dramatically different predictions for outgassing behavior, highlighting the fundamental uncertainties that plague attempts to understand interstellar objects through remote observation alone. The developing coma around the visitor remains invisible to optical telescopes, requiring sensitive ultraviolet and infrared instruments to detect the scattered light from dust particles and fluorescent emissions from excited gas molecules. These observations reveal a coma structure that expands symmetrically around the nucleus initially, then develops asymmetries as solar radiation pressure and the object's rotation create preferred directions for material transport. The coma's evolution provides real-time documentation of processes that models can predict only approximately, offering rare opportunities to test theoretical understanding against observational reality. Radio observations detect molecular emissions from the coma as outgassing liberates compounds that have remained frozen for millions of years. Water vapor produces the strongest signals, followed by carbon monoxide, methanol, and more complex organic molecules whose radio signatures reveal rotational temperatures and number densities within the expanding gas cloud. These measurements provide the most direct information available about the object's composition. As molecules recently liberated from surface ice carry chemical fingerprints largely unaltered by subsequent processing in the interstellar environment, the radio spectra show unexpected complexity, with multiple velocity components that suggest different source regions on the nucleus experiencing varying degrees of solar heating. Some emission lines display Doppler shifts that correlate with the object's rotation period, indicating that outgassing occurs preferentially from specific surface features that rotate in and out of sunlight with the nucleus's tumbling motion. This correlation between rotation and activity provides constraints on surface topography and composition distribution that optical observations cannot resolve directly. Perhaps most intriguingly, the visitor's outgassing behavior shows temporal variations that correlate weakly with solar activity rather than simply distance from the sun. During periods of enhanced solar wind density or elevated ultraviolet flux, outgassing rates appear to increase beyond levels predicted by purely thermal models. This correlation suggests that high-energy particles and photons may trigger chemical processes within the object's interior, perhaps liberating trapped gases through mechanisms more complex than simple sublimation of surface ice. The possibility of subsurface chemistry driven by cosmic ray interactions opens new questions about how interstellar objects evolve during their long journeys between stellar systems. If cosmic rays can penetrate sufficiently far into the interior to drive chemical reactions, then the visitor's current composition may differ significantly from its state at ejection millions of years ago. Such evolution would complicate attempts to use interstellar objects as pristine samples of conditions in distant planetary systems. Yet it would also provide new insights into chemical processes occurring in the radiation environment of interstellar space. Laboratory experiments attempting to replicate these processes face fundamental limitations imposed by the extreme conditions required, temperatures near absolute zero. Radiation doses accumulated over millions of years, and chemical environments dominated by materials that exist only in trace quantities on Earth. Researchers must rely on theoretical models calibrated against limited experimental data, introducing uncertainties that propagate through calculations and emerge as wide ranges in predicted outgassing behavior and chemical evolution. The visitor's response to solar heating occurs against the background of its continued orbital evolution, as gravitational forces shape its trajectory while non-gravitational accelerations introduce subtle perturbations that accumulate over time. The interplay between these effects creates a complex dynamical system where small changes in outgassing patterns can produce measurable alterations in the object's long-term orbital future. These coupling effects between physical chemistry and celestial mechanics illustrate the interconnected nature of processes operating across vastly different spatial and temporal scales. As volatile materials continue sublimating from regions warmed by solar radiation, the visitor begins its transformation from a dark, inactive wanderer into an active member of our solar system's population of small bodies. This transformation remains incomplete and temporary. Once the object passes perihelion and begins its journey back toward interstellar space, cooling will gradually suppress activity until the visitor returns to the dormant state it maintained throughout its millions of years of galactic wandering. The current period of activity represents a brief awakening, a temporary response to energy sources that will fade as quickly as they appeared. The outgassing continues with mathematical regularity, following physical laws that operate identically throughout the universe, yet producing results that depend sensitively on the specific materials and conditions that the visitor carries from its distant origin. Each escaping molecule represents a small piece of evidence about chemical processes that occurred in stellar environments far removed from our direct experience, delivered through the vast distances of interstellar space by gravitational forces that recognize no boundaries between different chemical compositions or planetary system architectures. Across Earth's surface, telescopes turn toward the visitor with the coordinated precision of a global scientific instrument, their mirrors and detectors working in quiet harmony to capture photons that have traveled from an object carrying the chemical memory of distant stars. The observation campaign unfolds with the patient methodology that characterizes modern astronomy, where individual measurements accumulate over weeks and months to reveal patterns invisible to casual observation. Each telescope contributes its specialized capabilities to a collective effort that transforms the visitor from a point of light into a detailed scientific subject. The Atacama Large Millimeter Array spreads its dishes across the Chilean high desert, listening for radio emissions that reveal molecular composition and physical conditions within the visitor's developing coma, at altitudes where Earth's atmosphere grows thin and water vapor interference drops to negligible levels. The array operates with sensitivity approaching theoretical limits imposed by quantum mechanics and thermal noise. The radio observations require integration times measured in hours to achieve sufficient signal-to-noise ratios. As the visitor's emissions compete against cosmic background radiation and terrestrial interference from communication satellites and electronic devices, ground-based optical telescopes equipped with adaptive optics systems track the visitor's brightness variations with photometric precision measured in millimagnitudes, changes so subtle that they approach the fundamental limits imposed by atmospheric turbulence and instrumental stability. The Large Binocular Telescope on Mount Graham uses its paired mirrors to achieve angular resolution that rivals space-based instruments, while the Keck Observatory's segmented primary mirror collects enough light to enable spectroscopic analysis of reflected sunlight passed into thousands of individual wavelength channels. Amateur astronomers worldwide contribute observations that professional facilities cannot provide, filling temporal gaps imposed by weather, maintenance schedules, and competing research priorities. Their smaller telescopes may lack the sensitivity to detect faint spectral features, but they excel at providing continuous photometric coverage that maps the visitor's rotation period and brightness variations with unprecedented temporal resolution. The collaborative network spans continents and time zones, creating nearly continuous observation coverage despite Earth's rotation and the unpredictable nature of weather patterns. The visitor's light curve emerges from this coordinated effort as a complex pattern of brightness variations that repeats every 7 hours and 38 minutes, confirming its tumbling rotation while revealing subtle asymmetries that hint at irregular shape and non-uniform surface composition. The photometric data shows 2 distinct maxima and minima per rotation period, consistent with an elongated object presenting different cross-sectional areas as it tumbles through space. However, the exact amplitude and shape of these variations change gradually over time, suggesting either surface features rotating in and out of view or evolution in the object's activity level as solar heating penetrates deeper into its interior. Spectroscopic observations reveal absorption features that correspond to specific molecular transitions in water ice, carbon dioxide, carbon monoxide, and more complex organic compounds frozen into crystalline matrices that preserve information about formation conditions. Each spectral line provides constraints on temperature, pressure, and chemical environment, allowing researchers to reconstruct the thermal history of materials that formed under conditions utterly different from anything experienced within our solar system. The spectra show evidence of radiation processing that occurred during the object's interstellar journey, with certain molecular bonds modified by cosmic ray interactions over millions of years. What puzzles astronomers is the apparent youth of some surface materials, which shows spectral signatures suggesting recent exposure to space rather than the radiation-darkened appearance expected after millions of years of cosmic ray bombardment. This discrepancy might indicate active processes that refresh the surface composition, perhaps through thermal cycling that brings subsurface materials to the surface or through micrometeorite impacts that excavate pristine interior materials. Alternatively, the visitor's composition might include materials that naturally resist radiation damage through chemical configurations that rapidly repair molecular disruption. Infrared observations from space-based platforms detect thermal emission from the visitor's surface, providing direct measurements of temperature distribution and thermal inertia that constrain models of internal structure and composition. The Spitzer Space Telescope, operating in the cold environment beyond Earth's atmospheric interference, achieves sensitivity sufficient to map temperature variations across the object's surface as it rotates. These thermal maps reveal asymmetric heating patterns that correlate with topographic features invisible to optical telescopes, suggesting a complex surface topology with varied thermal properties. The thermal observations indicate that much of the visitor's surface consists of fine particulate material with thermal inertia similar to lunar regolith, suggesting extensive processing by micrometeorite bombardment during its interstellar journey. However, certain regions show higher thermal inertia consistent with more consolidated materials, perhaps indicating areas where sublimation and redeposition of volatile compounds created cemented structures or where the original formation processes produced materials with different physical properties. These variations in thermal response provide indirect constraints on the object's internal structure and formation history. Polarimetric observations add another dimension to the analysis, as polarized light scattered from the visitor's surface carries information about grain size, composition, and surface roughness at microscopic scales. The degree of polarization varies with phase angle and wavelength in patterns that depend sensitively on the optical properties of surface materials. These measurements reveal that the surface consists primarily of dark, carbon-rich particles with sizes ranging from submicron dust to larger aggregates, consistent with materials that have undergone extensive processing in the interstellar radiation environment. The polarization data shows subtle variations that correlate with the object's rotation period, indicating regions of different composition or grain size distribution across the surface. Some areas display polarization signatures consistent with fresh ice exposure, while others show the characteristics of radiation-processed organics that have developed complex molecular structures through cosmic ray interactions. These compositional variations suggest either heterogeneous formation conditions or subsequent modification processes that operated non-uniformly across the object's surface. Professional observatories coordinate their efforts through their international networks that share observing time and data in real time, allowing rapid response to unexpected developments in the visitor's behavior. The International Astronomical Union's Minor Planet Center serves as a clearinghouse for astrometric observations that track the object's precise position and orbital evolution, while specialized working groups focus on photometry, spectroscopy, and theoretical modeling. The collaborative effort represents one of the most intensive observation campaigns ever directed toward a single small solar system object. Radio interferometry, using globally distributed telescopes, achieves angular resolution sufficient to resolve the visitor's coma structure and map the spatial distribution of different molecular species within the expanding gas cloud. The Very Long Baseline Array stretches across North America and beyond, creating an effective telescope aperture thousands of kilometers in diameter that can distinguish emission from different regions within the coma. These observations reveal asymmetric outgassing patterns that correlate with the object's rotation, suggesting that volatile release occurs preferentially from specific surface features. The radio maps show that different molecular species originate from distinct regions of the nucleus, with water vapor concentrated near the subsolar point, while carbon monoxide emissions appear more uniformly distributed. This spatial segregation suggests either compositional heterogeneity within the nucleus or different temperature thresholds for sublimation of various ice species. The observations provide rare opportunities to study the three-dimensional structure of cometary activity in an object whose composition reflects formation conditions in an entirely different stellar environment. Astrometric measurements achieve precision approaching micro-arc-second levels through careful analysis of the visitor's position relative to background stars, allowing detection of non-gravitational accelerations produced by outgassing forces. These measurements require sophisticated analysis techniques that account for systematic errors introduced by atmospheric refraction, instrumental calibration uncertainties, and the gravitational perturbations of solar system planets. The resulting orbital solutions provide constraints on the magnitude and direction of outgassing forces that complement direct observations of the coma. The combined dataset grows daily as observations accumulate from facilities around the world and in space, creating an unprecedented record of how an interstellar object responds to solar heating. Each new observation adds constraints to theoretical models while simultaneously revealing unexpected complexities that challenge current understanding of small body physics and chemistry. The visitor's behavior follows general patterns predicted by cometary science, yet displays unique characteristics that reflect its exotic origin and unusual composition. What emerges from months of intensive observation is a portrait of an object that bridges multiple scientific disciplines, requiring expertise in planetary science, stellar astronomy, galactic dynamics, and astrochemistry to interpret fully. The visitor carries information about stellar nucleosynthesis processes, interstellar chemistry, galactic structure, and planetary system formation encoded in its physical and chemical properties. Each measurement adds to this growing library of information while highlighting the fundamental challenges involved in extracting detailed knowledge from remote observations of objects that formed under conditions vastly different from anything accessible to laboratory study. The observation campaign continues with the methodical patience that characterizes modern astronomy, where significant discoveries emerge from the accumulation of precise measurements rather than dramatic revelations. Each photon captured by these instruments carries information across the vast distances that separate stellar systems, delivering data about cosmic processes that operate on scales ranging from molecular interactions to galactic evolution. The visitor serves as an involuntary messenger, carrying news from distant stellar neighborhoods while remaining entirely unaware of its scientific importance to the civilization that has learned to decode its chemical and physical signatures. The spectroscopic analysis reveals a chemical